All right, we are going to look at thin-walled pressure vessels today. So let me clear some stuff out of the way. Get that set to stay focused. Thin-walled pressure vessels. And we are making a distinction between thin wall and something like a thick wall pressure vessel. Once we get through some of the derivation of where these equations are coming from, you'll see why the thin wall is what we're doing. We're going to look at two types. Spherical. So something like a basketball, maybe a basketball falls into thin wall. It didn't actually measure, but it would be close to thin wall. It's got a relatively thick wall to how big it is diameter-wise, but it's probably in the thin wall range. It's not metal though, so that's going to create a whole new set of stuff. But we're thinking something like that. And cylinder or cylindrical. So something like an airplane fuselage or something like that, where it's a long cylinder with thin walls compared to how big it is. And on the cylindrical ones, the end caps do make a difference. We're ignoring all of those effects. So we're keeping it pretty simple and looking at something like a basketball and something like a Coke can is what we're thinking of here for our thin-walled pressure vessels. For them to be thin wall, we do have a little bit of constraint on how thin the walls need to be, and that's going to be the wall thickness divided by the vessel radius. That ratio needs to be less than or equal to 1/10. So the radius needs to be 10 times bigger than the wall thickness, more or less. And it's not there's not like a hard cutoff between thin wall and thick wall. But the difference is in the thin wall, well, there's two differences. One of them is an assumption we're going to make later on when we derive our equations for the pressure vessel stress. And the other is that in the thin wall, we're going to make the assumption that the stress in the wall itself is uniformly distributed. Whereas in a thick wall, something that's got a pretty massive wall there, the stress is not going to be the same from the inside of the wall to the outside of the wall. And so we would have to take that into account if we were thinking about a thick wall pressure vessel, which we're not going to do in here. So let's draw us some pictures and see if we can make some sense of this. So let's going to start with the spherical pressure vessels, and let's just imagine slicing a basketball through its diameter. So basically cutting it exactly in half. So you would have something like this. There's half of our sphere. Let's put a opening on it here, sort of like this. Now I'm going to draw it with relatively thick walls just so we have something to look at. But remember, it is a thin wall pressure vessel. So there's our wall. If we were to color it in, maybe that would help us out on figuring out where things are. So let's say that this blue is the wall. Now it doesn't matter if we cut any particular shape here, no matter which way you slice the sphere, as long as you slice through the diameter, it's going to look, you could rotate it to look like this. Now if you thought about slicing like the edge, maybe like slicing back here and slicing this edge off, you could do that. And it'd look more or less the same, except the ratio of wall to the inside would be different. And it would turn out that the stress in the wall there would be lower than the stress we're going to calculate here. This is the worst case way to slice up the pressure vessel if it's a sphere. So let's draw some of the stresses on here that we're talking about. So the stress that we're concerned with would be some kind of stress in this wall. If this stress gets too high, so I'm just drawing some little arrows that might signify the stress in the wall. We'll call that sigma A. If you want to, it's sort of an axial. I guess there's not necessarily a longitudinal axis here, but we'll call it the sigma A. And that's going to be the stress in the wall of the pressure vessel. Maybe we'll zoom into that to make it easier to see. So this stress, if it gets too large, will cause the wall to stretch out, to yield. It'll get a thin spot in it, and that thin spot will then bulge and then burst. And all this might happen instantly and it kind of explodes, or it might gradually happen and you get this bulge on the pressure vessel, or all of which are bad. So that's the stress that we want to monitor to make sure that this stress doesn't exceed the yield strength of whatever we made our pressure vessel from. This stress is caused because there is an internal stress. I'm going to draw this. Hopefully this shows up a different color. It is different, but let's make it more different. All right, you can see that different on camera. All right, so this is the inside. It's filled with some kind of fluid. Maybe it's air, maybe it's a liquid of some kind, but there's some pressurized material inside here, and we have basically kind of sliced it right in half, and we're looking at this surface of it. It is generating, there's some kind of pressure that is, we're in this case going to be pushing to the left. We'll draw a big arrow for that. So this pressure, we'll call it P. That's the internal pressure that is causing this stress in the wall to exist in the first place. So this is whatever internal pressure we're holding in this pressure vessel. And we're thinking of the internal pressure being larger than the surrounding air pressure. I suppose it could work the other way and you have a vacuum inside the pressure vessel. I actually don't know if these same equations would work exactly the same, but they would do similar things. But then you're really trying to kind of almost buckle the surface here. This is a tensile stress. So we're thinking of this being a higher stress than the outside. So like a basketball is, I don't know, 18 psi or something relatively small like that. All right, so we need a couple more variables. One, we need this distance. So this little distance here will be T, the wall thickness. And then we're going to have one other variable. And then there's a couple others that we might show up later on, but for now, let's just use this one. This will be R, and it's going to be the inside radius. So it might make more sense to have the outer radius, particularly if you're trying to describe, like if we were trying to describe the size of a basketball, we wouldn't really talk about the inner diameter of the basketball. We'd measure the outside of it. But there's a reason we're using the internal radius here, and it'll show up in a second once we get to it. All right, so we've got our variables. We need to remember the idea. Let's make some room over here. We need to remember the idea that pressure and stress are similar to each other in that they both, whether it's pressure or a stress, they both are some amount of force distributed over some area. Okay, and from this idea we can also say that, well, the force associated with this is just equal to the pressure times the area that it acts on. All right, so that's going to be important here immediately. So if we think of this internal pressure, the force associated with this internal pressure, so here this force associated with the internal pressure would be that pressure times the area that the pressure acts on. So we would have, let's just call it force associated with pressure, so P. We'll get all that on there. Force associated with P equals the internal pressure, which I've labeled as P, times the area that that pressure acts on, which is this green area here, pi r squared. So now we have a way to calculate the force associated with this pressure based on the pressure itself and the size of the pressure vessel. The stress, the wall stress, has a force associated with it. So let's do the same thing. So the force associated with the wall, we'll call it Fw. That equals the stress associated with the wall, sigma A is what I labeled that, times the area that acts on, so this light blue ring here. So the first thing you would think is, okay, well, I could do that pi r, if I had a outer radius here, r0 for outer or ro for outer. So pi ro squared minus pi r squared, that could be that area. So this term would be the area of that ring there, the blue ring. And that's totally fine, except that we're going to simplify it because we don't want these two different radius in here. We want to make things a little bit simpler, and we want to say that, well, this is a thin-walled pressure vessel, and so the outer radius and the inner radius are pretty close to each other compared to the size of this thing. So we're going to make an approximation. So here's what we're going to do. We're going to take our pressure vessel ring, so we had something like this. So this ring is this blue ring over here. So same thing. And this area would be the area that we're looking at right now. We could calculate that if we used this distance as that r outer and this distance as r. So that area would be calculated this way. What we're going to do is we're going to say that, well, let's just chop it open right here and flatten it out into basically this shape. And that shape is just going to be a rectangle where the thickness of this rectangle is the wall thickness T. So this dimension is T. And the length of this rectangle is the circumference of the ring here. And we're going to use the inner radius. We could use the outer radius or the inner radius to create that circumference, or we could like average them together and create like this average line. We're just going to use the inner one mainly because we use the inner one in this calculation. So the circumference would be 2 times pi times r. So now the area of this guy, this rectangle, is 2 pi r times t. So base times height is all it is. So we'll change our equation over here to say that the force in the wall is pretty much equal to sigma A times 2 pi r t. All right, so and as long as we stick with the thin wall idea, then this is okay because this area is really close to this area when it's a thin wall. Now what I want to do is, the way I drew these is kind of drew them all horizontal in maybe what you might call the x direction. And now I have forces in the x direction. So I'm going to do the summation of forces in the x direction for these two forces, the force from the pressure and the force from the stress on the wall, and say that they must be equal. If they aren't equal, then one of these is larger than the other one, and my basketball, if that's what I'm looking at, is exploding or imploding. But we're thinking of the exploding type of scenario. So summation of forces in x equals 0. We have, I drew the wall going to the right, so let's say this one. sigma A times 2 pi RT minus the force associated with the pressure. So minus P times pi R squared equals 0. Here is the stress I'm interested in solving for. That's the stress in the wall. That's the one I want to monitor to make sure it doesn't exceed the yield strength of the material I made this from. So I'm going to solve this equation for sigma A. So that basically just means move this to the other side of the equal sign and divide by this. So sigma A equals, let's do it one step at a time. So equals P pi R squared over 2 pi RT. Okay, so I've got the pi cancels itself out. And since I use the internal radius in both of these calculations, I have internal radius here cancels out one of those. And this thing simplifies to the stress in the wall of a spherical pressure vessel equals P, there's still one of these R left, so P times R over 2 times T. And that is what I'm interested in. So this equation would give me the tensile stress, so it is a tensile stress, it's trying to pull the wall apart, in the wall of a spherical pressure vessel. It is the maximum one. You know, I could have sliced this up somewhere else and gotten a actual smaller stress here, but this is the maximum stress in the wall of a pressure vessel, as long as the pressure vessel is spherical. So you could imagine using this equation to solve for this stress and compare that to the strength of the material for the pressure vessel. Or maybe you have an allowable stress and you want to figure out how thick the wall needs to be to solve for, you know, some factor of safety, to have a factor of safety or whatever. So it's an easy equation to use. We'll use it in a second once we've dealt with the cylindrical pressure vessels. Then we'll come back and actually put some numbers into here. But let's think about the spherical ones. Well, no, this is the spherical one. Let's think about the cylindrical ones. So the cylindrical one, if we're thinking about now we have a Coke can. And we could make this exact same free body diagram. The only difference would be instead of this being curved, it'd be kind of a cylinder back here. So one stress in a cylindrical pressure vessel would look exactly like this derivation. And we'd end up, and it would make more sense now, it's an axial, or maybe it's even called a longitudinal stress because it's along the longitudinal axis of the cylinder. And so there is this kind of stress in a cylindrical pressure vessel, but there's another kind also, and it's the other one we want to look at a derivation for. So let's back up a little bit and let's draw us a cylindrical pressure vessel like a Coke can. We'll lay it on its side instead of standing it up. I guess it could be, I don't know, I guess it could be upright too. Let's do it upright so it's like a Coke can. So let's, where are my ellipses? I think we were using these. All right, so let's use this. Again, we're ignoring the end conditions. Like if it is it rounded on the end, or is it like a cone, or flat like a Coke can? And we're ignoring that. So here's a potential cylindrical pressure vessel. And we could cut it through here somewhere, rotate that, and it would basically create this free body diagram with, you know, something like that on the bottom of it. But it would create the same exact free body diagram. So there is a sigma A equals, and it's either going to be called axial or maybe longitudinal stress in the wall of this, and it would look just like that. It would be PR over 2T. Same exact thing. T is the wall thickness, R is the internal radius of the pressure vessel, P is the internal pressure, and so it would be the exact same thing. But what if it was that we were thinking about it breaking. Oh wow, this will be interesting. Kind of like this. If I can find where the diameter would be. So we have a plane that cuts it like this. And it's going to cut through down there somewhere. Right there. So it's going to cut it apart right there. Right there. And we'll have this piece come away from this piece back here. Let's try and draw this piece. If I can do that. Let's see. That would look kind of like this. And we're ignoring the ends. We don't know what they look like. So we're kind of just ignoring them. And let's make sure we're all in the picture here. So this would be the wall back here. And then we'd have one right here we could see. And then this edge. And that comes around. And then same thing over here. And we need our little ellipse to draw. Oh wait, which one did we use? We used that one. Something like that. All right, so hopefully that makes sense of what we're trying to draw. We use this red plane to basically slice the pressure vessel in half down its length. So here's a Coke can. So we cut it this way, right? And over here, what would be the wall, the light blue part, you can probably zoom back in now, would be right here and right here. So this is the wall that is having to carry that wall stress. Now here, we're going to say that this, and let's see if we can get it kind of coming out this way, is not a longitudinal or an axial stress. We're going to call this a hoop stress. And these should all be parallel. I probably should try to be neater with that, but something like that. And then over here where we had the green area that was under pressure, the liquid or whatever, the fluid inside that was under pressure, that is going to be right here. So something like this. So a big rectangle. I don't know how fancy I want to be with getting this colored in solid, but something like that. All right. This internal pressure, like we had here, is going to act on this green area, and let's make it with the bigger arrow. Something like that. That'll be P, the internal pressure. And it's spread out over that entire area. I'm just drawing one arrow to show it. So we have this dimension, which we'll just call L for the length, or in this case it looks more like a height, but sometimes these are laying on their side and it looks more like a length. And then we have this dimension, which is the inner diameter, but we've been using that R, so let's just call it 2R. So the 2 times the inner radius. All right. Now let's do the same thing that we did before when we associate or find the force associated with the internal pressure and find the force associated with the hoop stress. So for the pressure, we have the force associated with the pressure equals the pressure times the area that the pressure acts on, which is 2R times L, just this green rectangle. And then for the hoop stress, we have the force associated with the hoop stress, which we'll call FH, equals the hoop stress, sigma H, times the area that it is spread over, which there's two of them. There's a light blue over here and a light blue over here. So there's two that are each, oh, I didn't label it. They each have, let's put it right here. Wall thickness T, right? So T times L, so width of T and a height of L. So 2T times L. And then we'll do summation of forces in whatever direction you want to call this. We'll call that the X direction. There we go. Summation of forces in X equals 0. So I've got the one with the hoop stress, which is FH. So sigma H times 2 times T times L minus the force associated with the internal pressure, P times 2 times R times L. Those have to add to 0 or else it is exploding. We're going to solve this equation for sigma H. Sigma H equals P2RL divided by 2TL. And then you can see the L's cancel out and the 2's cancel out. And I end up with sigma H, the hoop stress, equals PR over T. So very similar equation to what we used for the axial stress in both the spherical pressure vessel and the cylindrical pressure vessel, except that that stress had a 2 in the denominator, and here we don't. So the hoop stress in a cylindrical pressure vessel is basically twice this axial or longitudinal stress. But the equations are very similar. So normally if you're dealing with a cylindrical pressure vessel, you're going to be interested in the hoop stress. And if you're dealing with a spherical pressure vessel, you're going to be interested in the only one that we actually calculated, this PR over 2T, the axial stress in the wall. Both of these are tensile stresses, so we're going to compare them to tensile strengths. So let's look at one of these in action and see if we can solve, get some of those dots of ink off of there. All right, so let's set up something where we're going to solve a spherical pressure vessel type problem. All right. All right, so we're given that we're going to be working with a stainless steel pressure vessel. So that'll tell us something about the material properties we need to deal with. Oops. We're going to make this an annealed stainless steel. It will be spherical. It will have an internal pressure let's say 150 psi. And let's say we want to have a factor of safety of 3. Let's see if that'll work. 2.5. Let's do 2.5. And that's going to be against yielding. We don't want this to even yield, because once it starts yielding, then you're going to get a thin spot in the thing, which is going to increase the stress locally in that spot, and it's going to blow out. And let's say that the outer diameter of this guy is 10 inches. No, let's make it 20 inches. Let's make it bigger than 10. So 20 inches. All right. So that's what we're given. And we're going to find the wall thickness. All right. So we want to figure out how thick should the wall be to meet all of our design criteria here. So first of all, we need to figure out what our strength that we're working with is. So we need to know sigma y for this stainless steel. So we need to go to some charts of some sort. I have one over here that we can look at right here. And There's a stainless steel kind of in the middle of the page. There's one that is annealed and one that's cold rolled. We'll use, it said, the annealed one, and it looks like the tensile elastic strength, so the yield strength, is 36,000 psi. All right, 36,000 psi. But we don't want to use exactly 36,000. We want a factor of safety of 2.5. So our sigma allowable equals this 36,000 psi divided by our factor of safety, which is 2.5. So where'd my calculator go? Here it is. 36,000 divided by 2.5, 14,400. That's our maximum allowable stress in the wall. All right. Now we've got that, and we've got our equation. Sigma in the maximum stress in the wall of a spherical pressure vessel equals PR over 2T. So we just derived that equation for the sphere. All right, so our maximum stress that we're going to allow is this number, 14,400 psi equals P. It has to support 150 psi times R. We don't know the internal radius. We know the outer diameter and the outer radius, but we don't know the internal one. So what we're going to do here is say the outer radius is 10 inches, but we have to subtract off the wall thickness to get to the inner radius. So this probably won't make a huge bit of difference, but it will make some difference. So we're going to use this. If you use 10, it would probably be about the same anyway, but we're going to use the inner radius. 2 times T, that's the same wall thickness. So the only variable in this equation is the wall thickness, which is what we're trying to find. So we just need to expand this and do some little bit of algebra. So the 2T comes over here. 14,400 times 2 is 28,800 times T. I want to leave the units off. Everything's in pounds and inches over here so that my wall thickness should come out in inches. Here I've got 150 times 10, so 1,500. 150 minus T, so minus 150 T. And I need to collect these T together, so I need to add 150 T over here. So 2880 plus 150, I'm at 28,950 T equals 1,500. So divide 1,500 by that number, and we get 52,000. So T equals 0.052 inches. Now we should technically check and make sure that we don't have a case that it's a thick-walled pressure vessel. So remember, wherever we wrote it, if I can go back to our page, we said that the wall thickness divided by the vessel radius had to be equal to or less than 0.1, 1 over 10. So we have a wall thickness of 0.052 inches and an internal radius of, well, technically the internal radius is 10 minus this guy. 10 minus answer. So 9.948. That ratio, 0.052 divided by the 9.948 thing, is 0.0052. So we've got plenty of room before we get to having to worry about this being a thick wall pressure vessel. So we're definitely in the thin wall pressure vessel range. Maybe if we had, 10 times the amount of pressure, we'd get close at least, or 20 times, then we'd be over. But we're pretty good with the 150 psi. And normally you don't have even 150 psi is kind of high for a lot of these pressure vessels. So this is certainly reasonable, and we're not really in the range of having to worry with this being a thick-walled pressure vessel or anything like that. So I think we did a good job here with our pressure vessel design. We've got a factor of safety of 2.5 against the yielding strength of the material that we're using. And we've got a really thin wall. We could probably beef it up. And now what we would actually do is go find, all right, what is the standard size that is near this that we can actually buy and make a pressure vessel out of, which is probably actually pretty thick compared to this. This is pretty thin, 5 thousandths. Oh, no, that's not here we are, 50 thousandths. So even that's kind of thin, but that's a reasonable thickness. You could probably find a sheet that's 50 thousandths thick, but you wouldn't want 50, you'd want a little more than 50 thousandths because we need the 52 thousandths. Well, if you want to maintain that factor of safety of 2.5. All right, so that's all we need to talk about for thin-walled pressure vessels. Wednesday we'll come in and we'll talk a little bit about finite element method and how would you deal with stress concentrations if you didn't have the finite element method, if you have to do it by hand. So that'll be Wednesday, and that'll be the last topic for the whole course. So that'll be the last one that we do, and then we'll start over with something else in a few months, I guess, or a few weeks maybe. Maybe it's more like a few weeks. Anyway, one more topic in the statics and mechanics realm of things, and then we'll be done with it. I will see you on Wednesday for the last one of these.